Hello, everyone. I'm Riqiang Gao, a senior AI scientist at Siemens Healthineers. I'm so glad to share our research work about 3D dose prediction in radiotherapy. This work introduced a new game framework for dose prediction in heterogeneous context. The heterogeneous context means that the doctors and the planners may choose different types of plan and different beam geometry according to the location, size, and the shape of the tumor. Our GAN can handle multi-level conditions. Missing conditions may exist during the training and the test. We have an illustration experiment on the face dataset and detailed experiments on two radiotherapy datasets. So let's look at some details. Dose prediction can be broadly grouped to the image-to-image translation, as the predicted dose is also a 3D image. But it has some specific challenges. As the right button shows, the practical planning for lung cancer can have heterogeneous patterns, and there is no clear shape match between the source and the target. Most previous deep methods are limited to simple scenarios. This actually limits the usability of those approaches and makes them not generalizable in practice. So we propose novel conditional generative model, utilize additional information regarding the planning types and beam geometries. To have a precise dose prediction, two key points need to be addressed: individualism and realism. Individualism is required with a heterogeneous set of conditions. Realism makes the downstream tasks more manageable, as shown in the bottom right. A simple conditional GAN cannot satisfy our context, since we need to handle multi-level conditions with heterogeneous types, and missing conditions may exist during the training and the test. Let's look closer to the proposed method. Given M conditions and their missing indicator, we extend the loss function of the GAN in the format of this equation. To let the model be robust to missing conditions, we introduce missing consistency loss based on the condition regularization term. Basically, the MC loss reflects how predictions are consistent related to the observed condition J when another condition I is given or missing. The right button shows the experiment on the face images. We can specify 0 or 1 or 2 conditions during the generation with a single model. This is a framework for dose prediction. The input data includes the CT, PTV, OAR masks, and some other conditions, including the planning mode, the geometries, and the missing indicator. The inputs are fed into a generator to predict the 3D dose. Reconstruction loss and the SDV loss minimize the error between the prediction and the reference from different perspectives. There is a pre-trained encoder E together with a loss, cross entropy loss, regularizes the mode of the predicted dose, and a new MC loss is used to have the training. Specifically, the SDV loss is derived from the definition of widely used clinical term, DVH, to closely address the clinical interest. Here, the upper left shows 2 examples in different planning mode. Our experiments are conducted on heterogeneous lung cancer, including both IMRT and VMAT. 5 recently proposed dose prediction baselines are compared. 4 different evaluation metrics are included to compare the models. And we also have ablation studies of each component and a demonstration of the user interface. Here I show some of the experiment results here. Table 1 shows the comparison of our model with some state-of-the-art models in dose prediction. We can see that our model can achieve the best results in this heterogeneous context. Table 5 shows the ablation study of different components. We can see that our FC gain framework, the proposed SDV nodes, and the proposed MC nodes can make contributions separately. Figure 7 shows that our FC gain model can generate realistic 3D dose, even in this context. But if only use the backbone without the adversarial training, the prediction might be overfitted to a Gaussian-like distribution in this heterogeneous context. This page shows that our model can enable user fine-tuning with instant feedback. The mode and the angle planned are 2 types of conditions that can be modified. When given some conditions at the reference A, our prediction B has a reasonable match with the delivered dose, the reference dose. C shows that 3 conditional modifications with the desired prediction, even if a condition is missing. Finally, thanks to all the co-authors' contribution and the support of Siemens Healthineers. And thank you all for the listening. Thank you so much.